Thank you, Jose. 15 years of slam in 20 minutes. That's a bit of an ask. Actually, the depressing thing in the sense is that we haven't finished yet. But anyway, we had a lot of fun on the way. So I'll try and give you my view of how I saw this problem as it evolved. So to put it in context, let's look at what the problem is. So you have a robot with a bunch of sensors on it moving around in an unknown environment. The task is to come up with a representation of that environment and work out where the robot is at the same time. So put it a bit more formally, you have a vehicle which moves according to some kind of a motion model, so it's a dynamic system. You have a map which doesn't change, so it's a static. And you have an observation equation which relates what your sensors see to the state of the system you want to estimate, which is the combined location of the vehicle plus the map. This effectively, the best estimate is an optimization problem. So you either minimize the mean square error between the state and the expected, so it's a minimum mean square problem, or maximize the probability of X given a whole sequence of observations. So it's essentially an optimization problem. You can solve this in many different ways, and we saw a number of techniques evolved as time went along. The first thing, obviously, was to look at an estimate of the current pose of the robot plus the map. This is obviously a state nonlinear estimation problem with some dynamics in it, and the natural way to look at it is to look at something like the extended Kalman filter. So that's the classical solution. So we looked at that with quite a number of other people who are actually around here, Tardos and Castellinos, John Leonard's group, and Andrew Davison, and so on. So there have been quite a lot of work in this. And we managed to show some interesting results, some obvious but interesting. Say, for example, the map keeps improving. As you make observations, the map gets better and better. However, the map accuracy never exceeds the accuracy of the initial location of the robot. That is, you can't tell the difference between a map built in Chicago and map built in Sydney, unless you have some external pieces of information. When you look at the covariance matrix of the state estimate, it becomes gradually denser and denser, and that turns out to be quite a problem at the beginning, because the way to solve the problem is to invert this matrix, and that requires quite a bit of computation. It also turns out that these cross-correlations that gets built up as the map gets evolved are critical to the problem, and that's the kind of things that makes things like your loop closures work. So you can't basically get rid of them. After a little while, Sebastian and his group observed that the inverse of the covariance matrix actually contains a lot of small numbers. So it looks like a sparse matrix. It's not actually exactly sparse, but it's got very small numbers. And you can try and now exploit some sparse linear algebra to make this computation a little bit faster. But it's also turned out that even though these numbers are small, they are still very important. You just can't get rid of them. We saw some work from John Leonard's group, which basically did some tricks to make this exactly sparse. And that obviously made the computation a little bit faster. Another way to look at this problem is to solve for the whole trajectory. Now, this on the base of it doesn't look very sensible. If you're talking about a robot that has a sensor which is acquiring information at about, say, 10 hertz, this means every minute in 2D sense, you're adding about 1,800 variables into your state vector, and you think this shouldn't work. But it turns out that Frank Delatte and his group showed that the Jacobians and the Hessian in this associated optimization problem is very, very sparse. And you can indeed compute this very, very quickly, and you can solve this problem quite effectively. So this turned out to be, although on the basic simple look at it, intuitively it doesn't look good, but it actually turned out to be a very good solution. That was a big surprise at the time. So various people, including ourselves, looked at reducing the cost of doing this, estimating the whole trajectory. We looked at capturing the information between two poses into a local map. So you summarize the information contained in the system between two poses, and you can then forget about all the poses in between. And then you can start joining these things together using this what we call a sub-map strategy to build the map. And that is turned out to be a reasonably good strategy as well. A completely opposite way of looking at it is just looking at the robot trajectory only. Now, considering the fact that when we looked at the original problem, the map is the one that keeps improving. Map is the one that keeps the information. Again, this doesn't make good sense. Why do you now suddenly forget the map altogether and see whether a solution solve it? But again, to all of our surprise, this turns out to be a very effective technique as well, and this is probably the most exploited technique currently. And we had a student looking at the difference between just keeping the trajectory and the map together. And it also turned out that the difference is not big. So what you see here in green and yellow are the two trajectories coming from just the map, just the trajectory and map plus the trajectory. So again, against intuition, we realized that the trajectory actually keeps lots of information in there, which is a great thing in the end. We can do the same thing with just looking at the map. So you just you forget solving for the trajectory, you just try and build the map. And that turned out to be also a reasonably effective way of doing it. So we can see different solutions to SLAM evolved over the years with different dimensionalities. Most of these later solutions exploit sparsity. The information matrix is very sparse, and you can use sparse linear algebra tricks to do a good job. Recently, we've sort of pushed this along a little bit and found that SLAM can be separated, the nonlinear estimation problem can be separated into two parts. One part involving just the orientations. So the dimensionality now is just the number of poses. And then once you find the orientations, you can find the rest of the solution by solving a linear set of equations. That obviously looks very good, but the sparsity is lost. So you are not as fast as what you were in the other solutions, but now we are looking at some new ideas on how to maintain the sparsity as well, and hopefully a paper will come in ICRA if we can get it done. Another surprise we had is we looked at a very simple SLAM problem with 2 poses or 3 poses, and we found that theoretically there's only 2 minima. In this, when you try to solve this problem, there's only 2 minima, regardless of how many features you have. And one of which only appears when the noise level is very large. So it looks like there's only 1 minima, which is 1 minima in a nonlinear problem, it's a convex problem. And also we found that some of the techniques that have come out for solving SLAM, relatively simple strategies like applying one constraint at a time, you think that shouldn't really work, seems to still give a solution. So this sort of makes you think that there's some hidden structure in SLAM which we haven't really yet recognized. Just like the sparsities, there's something else. Even more surprisingly, Shudong, one of my colleagues, noticed that if you look at the SLAM problem for Victoria Park data, people who work in SLAM knows about this, got about 6,000 state variables. You initialize the nonlinear estimation problem with random numbers, and you still get a solution. And it turns out to be the true solution about 85% of the time. So you start from a random guess, and after a little while, it converges to the solution. This is, again, a very surprising result. If you're a general nonlinear problem, you'll always get trapped in a local minima. It does contain local minima, so if for some other scenarios, it goes into a local minimum. But in this case, 85% of the time, we manage to get the true solution. So what's happening in here? For some data set, this doesn't work at all. So this gave us an idea to look at whether there's a linear solution to SLAM. Is it very close to a linear problem? And after about 12 years after we started looking at these submaps, we finally, one of the students, Liang Xiao, discovered that you can join 2 maps with a simple linear operation. And the insight here is that if you have 2 maps which are at the same base coordinate frame, joining them doesn't involve any orientations. Orientation is what gives the nonlinearity to the problem. And therefore, this process can be made linear. And then once you join them, you end up with a map about this coordinate frame. You do a coordinate transform to transform the map into any arbitrary other coordinate frame. Now you can join another map built at this point into this one using a linear operation, and this can go on. So you can build a large-scale map. Obviously, some approximations are involved. When you build a submap, what you do is you solve an nonlinear estimation problem, and then you summarize the result by giving a state vector and its covariance. And that's obviously that's an approximation. So there's an approximation involved in here. So the solution you get is not the same as the maximum likelihood solution you'd expect. But it turns out that this approximation is very, very good. We tested it on many public domain data sets. The Victoria Park data set with different sizes of submaps. The DLR data set, some artificial data. The technique can be applied to post-SLAM or post-estimation. We test the Intel data set, Manhattan, and many others. So in the end, we think we found a solution that involved linear linear least squares to solve this problem. So it works with feature-based SLAM, post-only SLAM, and map-only scenarios. The formulation extends to both 2D and 3D. You maintain sparsity. You can deal with arbitrary covariance structure. There's no real issues there. There's no need for an initial guess because it's a linear least squares problem. And we get very good solutions for all public domain data sets. So we released the code in OpenSLAM. We're not sure exactly why all these are happening. We think the approximation is very, very good. And we know that it does the trick. So we are hoping that the community takes this up and we find out when it doesn't work so that we can have another look at what's going on in there. But it looks very good at this point. So we looked at two aspects. One is the linearity. One is the dimensionality, and the other is the linearity. There's another issue. You know, that SLAM is now solved pretty much as a graph problem. We've been recently looking at whether the graph structure can say something about the quality of the solution you can get. I'm going to have a 3-minute talk later this session to show some of the results we got in this area. So the three aspects, the dimensionality, linearity, and structure, turned out to be the three key insights we got into this interesting problem. Where to from here? I think, as I said at the beginning, although people have been talking about SLAM for maybe, John said yesterday, maybe about 25 or so years, and I've been involved for 15 years, and we haven't finished yet. I think there's still many more things to do. Currently, we are looking at active SLAM, especially given that if you can say something about the quality of the solution by looking at the structure, that means you can say something about what you're going to get without actually having to solve the problem. This is obviously going to be a great thing if you're trying to actively do some SLAM. What are the impact of your actions you can potentially evaluate by looking at what the kind of solution you're going to get. At the beginning, we solved the SLAM as one big problem. And after a while, if you look at the literature, now people are talking about a front end and a back end. This has done some very good things by allowing people to focus on fast solutions at the back end and leave the hard decisions about data association and things to the front. But in the end, you can make the front end much more efficient if you can exploit the information coming out of the back end to do the data association and things. I know that a lot of work has been done in Zaragoza about data association, and some of these things cannot be used if you don't think about it when you're doing the back end. I think this is something we are looking at to come up with an integrated solution now. SLAM in dynamic environment has been talked about for a while, but I think there's still some things to do there. And the environment representation. Although post-graph methods work very well, and we know empirically that not having a map is not such a big deal, I think it's still important to think about whether we can come up with a clever representation of the environment if the environment doesn't contain point or geometric features. So this is another thing we're looking at. So I think I've done quite well, actually. 15 years of SLAM in 15 minutes. So let me finish off by thanking many of the colleagues I had. So although I said at the beginning that I couldn't, it's depressing that we don't have a solution, but on the way I managed to work with a lot of very wonderful people. Say from Sydney University, with Hugh, who actually introduced me to SLAM in the late 90s, with all our students and his crew there. And then from UTS, after I moved over there, Shudong Huang and his students and my students and the colleagues who worked on the SLAM problem. So I'm really thankful for them, for the kind of results we are getting in this situation now. So let me stop there, and I still got 3 minutes plus to go, so I'm happy to entertain some questions.
Hello, I'm Keng Peng T from the A-Star Institute for Infocom Research in Singapore, and I'm here to present this paper on behalf of my colleagues who cannot be here today. So this work is about using a cognitive map and a direction-driven approach for robotic navigation. So the main objective of this paper is to investigate a direction-driven navigation approach, which mimics how humans typically navigate. So this is motivated by the fact that when humans navigate an environment, there is no need to record the details of the physical environment. And when traveling to a target destination, we tend to take directional guidance from another person or from a GPS. So our method consists of 3 components: a cognitive map building module, a grid-based direction planner, and a local navigation module. So the cognitive map is built using an RGBD-based red SLAM algorithm, which takes in RGBD and odometry data and generates a graphical map of discrete experience nodes. So when similar scenes are encountered by the robot, the 2 experiences are considered as the same, and a loop closure is performed. The direction planner extracts a path from the map and calculates the direction based on the current and the target locations. And lastly, the local navigation module takes care of avoiding obstacles, aligning the robot to the middle of a passageway, and also preventing the robot from entering dead corners. In our experiment, the robot successfully mapped a typical office environment, which consists of cubicles and labs. It is able to visit all the target destinations consecutively. Here, the cognitive map obtained is superimposed onto the floor plan of the office, and we see that the mapping is accurate. The red dots are actually the target locations, and the black stars are the decision points at which the direction of motions are extracted. So the mapping results can achieve about 99% precision rate and about 60% recall rate. These are the navigation results. So in the middle, we have the cognitive map. It's not very clear here. So on the right, this figure, it shows that the robot successfully navigated from point A to point B and the correct decision is made at the 2 junctions encountered along the way. And the left figure shows similar results, but for navigation to multiple destinations. So it's also shown in this paper that the robot is able to navigate a farther distance and with a faster speed, thanks to the lower computational load of the proposed algorithm. So with this, I thank you for your attention, and I look forward to speaking with you at the interactive session. Thank you.
Hello. So I'm Frank Dillard. I'm at Georgia Tech, and I'm presenting work here by my student, Young Dian. Jian, he graduated, went to Baidu, said, Frank, you can do the talk, right? So here I am, presenting his work. So you're all familiar with SLAM, simultaneous localization and mapping. And in my group and many other groups, we've looked at SLAM as a large optimization problem in a sparse factor graph. So you have some variable nodes, that are landmarks, and you have some nodes that are the position of the robot, and this is a very large nonlinear least squares problem that you're trying to solve. Now, some state-of-the-art solvers, one that we developed in our own lab is ISAM, which is incremental smoothing and mapping. It allows, to reason about the posterior probability over the map in an incremental fashion. But it does not scale so well as we would want with the number of loop closures. Yongdian, in collaboration with me and others, we have developed a batch method which uses a subgraph of the large sparse graph and uses it as a preconditioner in a conjugate gradient framework. And that's called the subgraph preconditioned conjugate gradient framework. We've shown this in robotics, but Yongyan also has an ICCV paper on this, which shows it working on very large-scale structure from motion problems. So the question is, how can we marry the benefits of having these good preconditioners that use subgraphs and the incremental nature of smoothing and mapping that we get from ISAM? So this paper is really about iSPCG, which is the combination of ISAM and SPCG, and combines the best of both worlds. So if you compare it to related work, we get both an algorithm that's both efficient, consistent, and optimal, right? And there is some other ways that you can have incremental methods, and I can talk in detail at the interactive session. Our results show, right, that we, with this iSPCG, which creates a sparse subgraph incrementally and uses periodic smoothing updates when the sparse subgraph doesn't give you good error anymore. The error is comparable to ISAM, but the computation time is somewhere between ISAM on this smaller and faster but suboptimal graph and ISAM on the full graph. We've shown results on some real data sets, and we have a measure of complexity of a data set, and iSPCG performs well for complex data sets. So I'll be happy to talk to you more at the interactive session. Thank you.
Good afternoon, everyone. My name is Khalid Youssef. I'm a PhD candidate at RMIT University in Australia, and the topic that I'll be speaking about today is real-time RGBD registration mapping in textureless environments using ranked order statistics. So the main idea is using a full dense point cloud is computationally expensive for registration and mapping, and particularly for real-time applications. Therefore, we propose an informative sampling scheme that is able to select only a subset of points that carry the most useful information for registration using the statistical analysis of their flatness. So this results in significant computational time reduction while achieving very accurate registration that's very comparable to using the full point cloud. So in order to do that, first we estimate the normals at each point in the point cloud, then we calculate the angle difference between that point's normal or each point's normal and the normals of its surrounding neighbors. Then we average those angles and we insert it into a residual vector, in which then we sort the residual vector in ascending order, and we plot the results here as shown in this example. So the sorted residuals are shown in the blue curve, and the main idea here is that those points included into group number 1 are the points that have normal orientations that are very similar in comparison to their neighbors. Those are the points that most likely lie in flat surfaces and are ill-conditioned and not very useful for registration because their normal orientations are very similar to the orientation of their neighbors. Whereas points included in group number 2 with higher value residuals are the ones that have normal orientations that vary or are unique in comparison to their neighbors. So there's a point that have some significant local curvature and the points that we call ranked order statistics features and the points that we use for registration. However, in order to obtain those points, we need to find the transition point, K prime, that separates the two segments. And for this kind of segmentation, we use the highly robust estimator called the modified selective statistical estimator. We then match those features that we just obtained with the ones obtained extracted from the previous frame using their assigned 3D descriptors and a mutual consistency check. And then those matches are refined since sometimes they contain some outliers. So we refine them using, again, the MSSE and the 6 degree of freedom transformation model. The relative transformations are concatenated up to the current time frame in order to obtain the current global pose. And finally, we use a global optimization step in order to accommodate for the accumulated drift or error that was caused by the previous method. So every time a loop closure is detected, additional constraints are added to the post graph and the graph is re-optimized. Here we show the results of the 3D mapping. So we rotated the Microsoft Connect 306 degrees back to its original position in an office environment. And this is only using the ROS features, so only the sparse subset of points that we extracted, about only 100 matches between the frames. As you can see, the results are very accurate and very fast. I'll be more than happy to discuss this with you in further detail in the interactive sessions followed by this presentation. Thank you very much.
Hello, my name is Mathieu Labbé, and I'm a PhD student at the University of Sherbrooke. My supervisor is François Michaud, and I will talk about the online global loop closure detection for large-scale multi-session graph-based mapping. So in this paper, we focused on the practical problems of mapping on a real robot with limited resources. So the first motivation is multi-session mapping. It happens very often that we need to reboot the robot or move it offline in a different location. So we'll just want the robot to know itself when creating a new map and when to merge it to our previous sessions. And the second motivation is to do all of this online and independently of the size of the environment. So for multi-session mapping, we tightly base our SAM approach on a global loop closure detection approach, which can detect not only loop closures in the current sessions, but also between the sessions. So when a loop closure is detected between two sessions, a new constraint is added in between the graphs, and the optimization algorithm will merge automatically the sessions together. Here an example of mapping the third and fourth sessions of our experiment. When a loop closure is detected with a previous session, the old maps will reappear in the current map. Detecting more loop closure between the sessions will add more constraints to the graph, and more constraints will be used for graph optimization. For large-scale online mapping, the problem is that processing time and for the loop closure detection and graph optimization is dependent of the size of the environment. So to respect the online constraints, we use a memory management approach that will limit the number of locations in the working memory of the robot for loop closure detection and graph optimization. So on the left, the memory management approach is activated. We can see the biggest map that can be processed online. The robot will forget some locations to respect the online constraint. And however, when returning to a previously visited area, the robot will remember forgotten locations, so more loop closures can be detected. So after the 5 sessions, here are the final global maps with and without memory management. The quality of the map is similar, but with memory management, the approach is, respects the online constraint. So I will be pleased to meet you in the interactive session to discuss more about challenges in online large-scale multi-session mapping. Thank you.
Good afternoon. I'm Luca Carlone. I'm a postdoc in the group of Frank Dellert, and I'm going to present our paper that is called Selecting Good Measurements VL1 Relaxation, a Convex Approach for Robust Estimation of a Graph. It's a joint work with Andrea Censi from MIT and Frank Dellert. So before starting, let me give you some context. Of course, I'm not going to tell you what is simultaneous localization and mapping. You know very well what it is. In this work, we consider a state-of-the-art formulation for SLAM that is called post-graph optimization. So in post-graph optimization, essentially, we try to estimate the trajectory of a mobile robot. So you can visualize the problem as a graph in which the nodes of the graph are the robot poses we want to estimate, and the edges in the graph are relative measurements, relative pose measurements. So in post-graph optimization, we compute the poses by solving an optimization problem in which we look for the trajectory x that minimizes the residual error with respect to the measurement zeta. Okay? In this work in particular, we care about the case in which some of the measurements in post-graph optimization are outliers. For example, the red measurement here. For instance, this happens when the robot is traveling in 2 different places that look similar. So it tries to enforce a constraint that is wrong between the corresponding poses. Why this is important in practice? Because we try to solve post-graph optimization. If there is no outliers, after a few iterations, we converge to a very good solution.
However, in presence of few outliers, the solution gets very messy. So essentially, discarding outliers make the difference between a correct map and a very bad map that you cannot use for navigation. What we propose, so how to detect outliers. To evaluate the quality of a set of measurements, we ask a very basic question. Does exist a trajectory that explains the set of measurements? So in equation, does exist a trajectory x that induces a residual error with respect to the measurements that is smaller than a threshold beta, for example, a 3 sigma bound? If the answer is yes, we say that the set of measurements is coherent, and in our approach, we just look for the largest set of coherent measurements. So the setup is very simple, actually. We use a decision variable that is binary, and if the decision variable after we optimize is equal to 1, we discard the measurement as outlier. If it is equal to 0, the measurement is inlier. We show how to relax in the planar post-graph optimization case this problem to a linear optimization problem. So we get a solution that is optimal, very fast, and scalable. We test our approach on a bunch of benchmarking problems where we get very good results, so we are able to reconstruct the correct trajectory of the robot also in presence of large amount of outliers, like 1,000 outliers on many benchmarking data sets. And even in a MATLAB implementation, this algorithm is very fast, so we can solve large problem instances in a fraction of a second in MATLAB. So I'll be glad to show you, take questions and show you many, many results during the coming interactive session. Thank you.
Hi, I'm Alex Siegel, and this is work with my advisor, Ian Reed, and it's about hybrid inference optimization as a way to deal with discrete variables in SLAM, specifically for robust postgraphs. So the long-term goal is, can we extend SLAM to deal with richer information than just geometry, has been addressed a few times already. So moving objects, changing environments, detecting sensor failures for longer-term autonomy. And in general, can we add all sorts of different discrete variables into the SLAM problem and take them into account when solving for the trajectories in maps? So in this paper, we try to come up with a way to do this and test it on postgraph optimization by trying to identify incorrect loop closures. So as a summary of postgraphs, you're given a chain of robot poses, they're connected by measurements. Occasionally you get a loop closure, and you want to try to optimize all this to get a map out of it. And the problem is, if there's even one incorrect loop closure, this will break the whole system. So the non-robust way of doing it is to be very conservative with when you add loop closures, and then use something like Gauss-Newton. It doesn't have to be Gauss-Newton, but the basic idea is almost always that you linearize at some point, you get a least squares problem, and you solve it, and you iterate. And this can't really deal with outliers very well. So there's all sorts of ways to deal with it, but this is one particular one that works well. So the idea is, each time you linearize, you get a sparsely squares problem. And a sparsely squares problem is equivalent to Gaussian MRF, which has been explored in ISAM works. And the work that we're doing here is basically adding discrete variables to this MRF. And in this case, it's inlier or outlier for each loop closure constraint. And the result is a hybrid graphical model, and we come up with an approximate optimization inference algorithm that uses message passing to solve this problem and find a new linearization point. So the main idea here is that if you do it this way, the discrete variables are taken into account inside the inner loop of the optimization algorithm. So you're not reweighing outliers and inliers after solving the least squares problem. As you're solving the least square problems, you're trying to find which discrete variables can I switch around to find the best value of the rest of the continuous variables. And you're doing this somewhat jointly. And so the results of this on the robust postgraph estimation data sets are state-of-the-art and fairly competitive. And the technique is fairly general, although it's a local optimization technique, but it seems to work pretty well. And hopefully there's other applications for this. That's it.
Hi, I'm Yasser Latif, and this is the work that I've done together with my supervisor, Jose Nera, and my colleague, Cesar Cadena. So continuing with the theme of robust backend for SLAM. So this is the problem that we are trying to solve that has been addressed in the previous two talks. So you have a front-end place recognition system, but it can make mistakes. In the worst case, it can give you something like this. So this is a robot trajectory shown in blue, and all the red links represent loop closures. The problem that we are trying to solve is to go from this side to this other side, where you have only the correct loop closures. And as we have seen, for example, in robotics, as well as in vision, that good data sets lead to an improvement in state of the art. So following along those lines, our contribution in this paper is a data set specifically designed to test robust SLAM backend algorithms. So what we did was we took 7 trajectories from the very well-known Kitty data set, and we extracted stereo visual odometry on 7 of these trajectories. So 6 of them have loop closures, and 1 of them does not contain a loop closure. Next, we proceeded for each of these trajectories to extract different sets of loop closure hypotheses, because this state-of-the-art algorithm that we use, it has a confidence parameter which you can move. And if you move that parameter, you can get something accepted on very low evidence or on very high confidence. And with this, you can generate different sets of loop closure hypotheses. Now, for each of these experiments, we manually annotated the ground truth, because depending on the parameters, you may detect some loop closures in one experiment, and you may not detect the same in others. So for each of these experiments, we generated manually annotated ground truths. So now you have 7 × 21 data sets on which you can try your algorithms. And how do we compare these? So we use the normal things. So for example, precision, which is the ability to differentiate between correct and incorrect loop closures. Your recall, which tells you how many of the correct loop closures you have recovered, and the absolute trajectory error, which in a way tells you the relative importance of the loop closures that you have recovered. And we also propose plotting this something like this. So this is if you accepted all the correct loop closures, this would be the error you would have. If you rejected all loop closures, then this would be the error you have. If you accept something incorrect, then you would go above this bound, and that is not a good thing. And then we tested it on many different available algorithms. This data set is publicly available. If you want, you can take a picture of this QR code, and you can come talk to me.
Hi everyone, my name is René Wagner. I'm going to talk to you about GraphSlam with signed distance function maps on a humanoid robot. This is joint work with Udo Frese at the University of Bremen and Bertolt Bäumel at DLR. So the motivation behind this work is that we want to perform localization and environment modeling on a humanoid robot in assembly and construction tasks as depicted on the right. The problem is that we've previously used Kinect Fusion for this, which generates nice, dense geometric environment models, but can fail irrecoverably at sensor tracking whenever the environment geometry fails to constrain the sensor hose sufficiently. However, in this situation, other sensors could help when the Kinect alone gets lost. We have a pretty good odometry on the robot. We have lots of position encoders throughout the kinematic chain, and we have 2 IMUs. We'd like to use these and model them using sparse parametric GraphSlam, which is very good at handling sensor data from a variety of sources, but cannot directly handle dense data like Kinect Fusion does. So how do we combine the two? We propose to split the world into overlapping local TSDF submaps, as indicated by these rectangles on the right. We attach these to the SLAM graph by reference nodes. That's the pose of each of the submaps' origins. And we then translate the Kinect Fusion ICP results into SLAM links. SLAM is the GraphSlam framework we use. And we then model the rest of the robot using regular GraphSlam techniques. For now, that's odometry, but we intend to use a more sophisticated model later. Now, the cool thing is that the GraphSlam optimizer can now modify the dense map by moving just these sparse reference nodes around. So let's see this in action. We've evaluated this on a 50 meters loop in our lab building, as shown in the panoramic photo at the top. And at the bottom is the graph optimization in progress. And you can see that the loop over here, this corner after a couple iterations matches quite well. That's a start. And after only a few iterations, we get a nicely consistent global map. And if you'd like to know more details about this, I'll be happy to talk to you later in the interactive session. Thank you very much.
Okay, so good afternoon, everyone. I'm Guillaume Tréhard, and I'm going to introduce you to Credibilist Simultaneous Localization and Mapping solution. It's a solution we have developed with my team at INRIA in France. We are actually working on autonomous driving in urban context and without any prior knowledge of the environment, so no pre-recorded map. And the solution we have developed is a grid map-based SLAM with a LiDAR input. And we are facing like the classic ambivalence of this topic, meaning that SLAM algorithm assume static input as landmarks, and urban scenario can have like a really crowded situation. And to bypass the classic static word assumption, we are proposing to switch from the probabilistic model to a transferable belief model, which comes from the evidential theory. And this framework is actually known as a richer representation of knowledge because it has an explicit representation of the not known information, which is really adapted for a LiDAR input. So in the following picture, it's the blue color. And in addition, it has a management of incoherent information through the time, which is called conflict. And actually, this conflict is generated from mobile obstacles and false alarms. So by having a management of this conflict, the TBM framework provides a way to weight the impact of mobile obstacles and false alarms in the SLAM process. So if I just have to roughly plot all the SLAM algorithm on a mobile object consideration scale, I would say that the classic SLAM algorithm are under a static word assumption. It's obviously like a roughly way to classify it, but just in order to show my point. And if you want a mobile object tracking, you will have to add some algorithm. And our solution is kind of in between because we don't have a mobile object tracking, but we are not under the static word assumption. So to prove the concept, we have designed a maximum likelihood SLAM using occupancy grid, and we have tested it over 10 sequences of the Kitty database with pretty good results. So here is just like a quick example, and I would be glad to answer your question and to provide you more information in the interactive session. Thank you.
Hello, I'm Disa. I'm going to present some results we've seen recently about the impact of graph structure on SLAM. It's primarily work by Kasra, who is a PhD student who is working with Shudong Huang and myself. So as we've seen in many of the presentations here, so you pose SLAM as an estimation problem over graphs. So SLAM problem nicely lends itself to a nice graph, whether it's a feature based problem or just on the post graph, it's a nice graph structure. The question we want to ask is that we know that the connectivity between these nodes actually is what makes the problem solvable. And how important are these connections? Or can we say something about the connectivity to the results you get if you try to solve this problem is what we wanted to ask in this paper. So the quality of the solution is related to graph structure. So here are two data sets with the same kind of noise model, but here the connectivity is not that good. And we ended up with a solution which is not really great, and here the connectivity is good and the solution is great. So the question is what can be said about Xtub just by looking at the graph rather than trying to solve the whole problem, which if we could do that would make life a lot easier when you're thinking of doing things like active SLAM or graph pruning. And then that's this result we are trying to present. So let me go to this. This was inspired by work from Olsen and Case, who presented in the RSS, basically showing that the average degree of the graph has an impact on the quality of the solution. So what you see here is this is the objective function, the value of the objective function at the optimum you compute. And this is the value of the objective function at the true solution. And if you get the solution right, both of these got to be the same, and you end up with the ratio of 1. If you end up with a solution which is not really great, this number actually is bigger. So you get a number bigger than 1, number smaller than 1 all the time. And these guys showed empirically that this is actually true, and showed a very nice graph in RSS a couple of years ago. And what we've done is to, based on some assumptions, come up with actually an analytical solution to show that what they demonstrated empirically is actually can be proven theoretically as well. And on top of that, Kastra managed to show that there's a very good strong relationship between the Laplacian of the graph and the Fisher information matrix that comes out of the solution. And obviously, this leads to a number of other results as well. One is the diameter of the confidence ellipsoids, and the volume of the confidence ellipsoids is related to the number of spanning trees of the graph. So we got quite a number of results showing that what we predict and what we actually generate are very similar. I'll be very happy to answer questions.
Hello, everyone. My name is Akbar. I'm from RSJ University, Toronto, Canada, and today I'm going to represent my work over a robust model predictive control for visual servoing. So visual servoing, as many of you may know, is actually the method to guide the robots using the camera images. Basically, what happens is you use the camera images at each time and compare it with the desired camera image to guide the robot to that desired pose. There are several challenges in the visual servoing systems, which some of them has been pointed out here. So the first challenge is actually this system is sort of constrained. The constraint is coming from the robot by some point, because the motion of the robot is restricted by the limited reachability and also the velocity and the acceleration of the system. In addition to that, there are some limitations coming from the camera, which has a limited field of view. For example, if you see, here is a picture from a camera, and here is actually another picture of the same scenery, but the camera has moved. They're not much alike here, but you can see there are some points that actually is being used in both actually images, but the camera has been moved, and you're losing some of the part of the image just because the camera has a limited field of view. So the other part that actually infects our system is the uncertainties of the system, which we are going to discuss next. So what we have presented here is actually a system that is composed of 2 steps. This controller actually tried to minimize the error before the servoing using an error-free model. And for that matter, we are actually using a model predictive controller to handle the constraints. Here we try to minimize the error of the features compared with the features of the desired image, and we have the set of constraints for the image space, in the image space, and also the camera velocity to handle the constraints for the Cartesian space. Basically, then after having those trajectories, we're using a simple controller to follow the trajectories using the camera velocity that we have computed, and also the features that we have before. So the problem that we have seen here is that the uncertainties of the system is affecting the system. Here in this picture, the red circles are showing the trajectories that are working in different simulations. And you can see some of the trajectories going in these red circles actually are crossing over the boundaries, so the path is actually working quite fine. So the solution to that problem would be some constraint handling based on some error modeling that we have developed in our previous work. So if we know how much this error is actually at each time of this trajectory, we can handle this constraint quite efficiently. So this is actually what we have done in our work. So here is this uncompensated system, and we try to tighten the constraints in a way that the trajectory is now not going past the borders. As you can see, this method is quite efficient. I would like to actually discuss the more details of this method now, but my time is limited, unfortunately. So I would like to invite you to join me in the interactive session. Thank you.
Hello, I am Kostas Kyriakopoulos, and I'm going to present the joint work with my colleagues from NTUA in Greece on issues of prescribed performance, image-based visual servoing, under field of view constraints. So it is well known that the image-based visual servoing is based on tracking certain features on the image plane. In order to be able to do that, those features should never be lost from the image plane due to the field of view constraints of the camera. Several solutions have been proposed for this, like the model predictive control approaches or the 3D path planning and projection of the image plane or optimization methods. But most of those methods suffer from computational complexity, which is very difficult to implement in real time. The basic idea that we want to pass through that work is the fact that we are defining the errors between the desired positions of the image plane, and those errors, we try to bound them in the transient and also to bound them with respect to the field of view constraints. In such a way, we have also good transient performance and steady-state performance. At the same time, we don't lose them on the, due to the field of view. So the basic idea then results in a control scheme like that, where L is the transmission matrix, and this is an appropriate function of the error. And this idea is based on an error transformation that makes the original constraint problem to an unbound and unconstrained one. The resulting algorithm is very computationally efficient, and it can be applied in real time, and we have applied that. Today we are going to show, and later on I'll be happy to show that more extensively in the meeting room on a manipulator, but we have applied that to other devices such as aerial vehicles and also mobile vehicles and underwater vehicles. Here we are going to show the manipulator trying to track 4 points and stabilizes them. They are on the board, and soon we are going to see that this stabilization, this transient performance follows the constraints that we have put, and we see them plotted here. I don't know if it's appeared very well in the transients that we have prescribed without tuning appropriately the gain. So it's a prescribed performance without trial and errors.
And I'm going to present my paper about monocular template-based vehicle tracking for autonomous convoy driving. The main goal of my work is vision-based autonomous convoy driving. You can see a convoy consisting of 2 autonomous vehicles and 1 manually driven vehicle in the upper image. Our autonomous vehicles handles the steering, the throttle, the brake, and the gear shift fully autonomously. As we would like to follow the convoy leader's path as closely as possible, we need an accurate estimation of the leader's position and orientation. So I'm going to talk about the vehicle tracking system today. It is based on 3D template models. Building a 3D template model consists of 3 steps. The first step is to capture 3 or 4 orthogonal views of the vehicle side. Then we detect prominent features like the red rear lights or the license plate. And finally, we train texture-based classifiers once per vehicle type in an offline step. The 3D template models are used for vehicle detection and scaled unscented Kalman filters used for tracking. The Kalman filter predicted 3D vehicle pose is projected into the image plane and resized to apply image processing in a smaller image area. Here visualized with a gray bordered rectangle. Then we remove unnecessary image information by using dynamic region growing. The trained texture-based classifiers are used to detect the vehicle sides, and the features from the 3D template model are used to refine the classifier detections. The unscented Kalman filter is used to estimate the 3D vehicle pose, to estimate the velocity, and to estimate the steering angle of the local convoy leader. The tracking algorithm is compatible with different vehicle types. We tested the algorithm against different weather conditions and illuminations, and we tested the algorithm against partial occlusion. The tracking algorithm runs in real time with a precise pose estimation, which allows convoy velocities of up to 28 meters per second. I would like to talk to you in the upcoming interactive session, and thank you for your time.
Hello, I'm Carl Pauwels, and I would like to present our work on real-time object pose recognition and tracking with an imprecisely calibrated moving RGBD camera. So we're considering complicated visual servoing scenarios, such as the one here, where you have a robotic arm and hand that's trying to pour a bottle into a cup. So the cup is being moved by a human, and also the camera is moving in this scenario. So there are many objects of interest that need to be tracked with very high precision in order to do this. So our tracking approach relies on a continuous real-time interaction between visual simulation and visual perception. And this all happens inside the graphics processing unit. So there's a lot of feed-forward and feedback communication going on between rendering and extracting optical flow and low-level vision. So the advantage of this is that our tracker can scale to hundreds of objects in real time. We can track objects and manipulators jointly. And because we have a 3D scene representation, occlusions are also handled implicitly. We also have a special region of interest approach that allows us to deal with sloppy calibration. So we use input from a Kinect, color data, and the depth signal. And we can render tracking hypothesis in great detail. So for example, we can render the texture. We can blend this texture with the actual color signal. We also use this as a visual cue. We know where all the segments are, and because it's 3D, we are aware of all the occlusions. We can synthesize the depth of the scene. This is thresholded here. And we also can synthesize a normal, so we use all this for ICP style registration. And we can also synthesize arbitrary viewpoints, so here to see that the servoing is very accurate. So here you see the system running in, well, this is a real-time visual servoing experiment, and as you can see, the servoing is being done more or less okay. The camera is also moving, and as you can see, the precision of tracking is very high at the interaction, like the occlusions between the bottle and the hand, they are very precisely segmented. This is critical for correctly assigning the low-level vision to the correct segment. So here the camera motion was kind of moderate, but in this next video we just show you the limits of the system. So, and here we're walking around the scene, and the object is also much further away. And there's also a large occlusion happening here. So we're currently preparing a open source release of this tracker, and that should be coming soon. So I thank you, and I hope to see you in the interactive session.
My name is Komamoto Oka. Let me talk about our research entitled Robust Ground Surface Map Generation using Vehicle Mounted Stereo Camera. Our goal is to build an off-road 3D ground surface map from stereo image sequence captured by nearly front-looking stereo cameras. At each time instance, we estimate 3D ground surface and camera ego motion. In our approach, the ground surface is represented by the vertex height of a regular grid mesh, which is friendly to mobile robot applications, such as traversable area detection and path planning. In this figure, we show the traversable area by blue patches, which indicate level areas on the ground. This is actually a challenging task, because the ground surface is highly slanted with respect to the camera view direction. Then, the front parallel assumption widely used for stereo vision cannot be held in this case. Moreover, we have to handle bumpy camera motions and illumination changes in real situations. This is an overview of the proposed method. At each frame, we minimize this cost, composed of a photoconsistency term and smoothness constraints term. To estimate a ground surface Z, egg motion mu, and brightness difference alpha from two stereo frames, the surface parameter Z indicates the vertex height of the regular grid mesh defined in the ground coordinate system. The brightness difference parameter alpha denotes the gain and bias between two images. This flowchart shows the process flow at each frame. First, a ground surface is estimated using only two stereo images. Second, we estimate an egg motion and generate a pixel mask using only consecutive two left images. Third, the ground surface and egg motion are defined using all images. Finally, we update the ground surface map by the estimated ground surface and egg motion. The method combinationally uses feature-based and pixel-based approach for robustly estimating egg motion parameters, while successfully handling self-shadows and bumpy camera motions. Please come to our interactive session site for more details. Thank you.
Oh, yes. Right. Now I'm Masum Lim from Korea Institute of Science and Technology, and I'm going to talk about our paper, RGB fusions, real-time robot tracking and dense mapping with RGB data fusions. Real-time 3D reconstruction of real scene play an important role for robotics and human-computer interaction. Kinect Fusion shows a remarkable result on accurate and dense surface reconstruction using a Kinect sensor and commodity graphic card. Kinect Fusion works well in a wide range of novel scenes. However, it fails when geometric features are insufficient. For example, a large planar scene or a circular object. This is because Kinect Fusion depends on ICP-based tracking. To handle this problem with ICP-based tracking, we present RGB fusion, which integrate both color and depth images into the color volume and use them for photometric tracking and geometric alignment in the frame-to model tracking. In the proposed tracking method, we first find the corresponding to the feature point between the input color image of the current frame and the rendered color image of the previous frame, and then find the relative rigid transformation between the input current frame and rendered previous frame using the 3D positions of the corresponding point pairs. For the robustness of the tracking, we also select the tracking method either ICP or proposed according to the scene geometry. The ICP-based tracking is preferred in the general case, but the proposed tracking method is selected when we don't have sufficient geometric features. The geometric richness is measured using the condition number of the linear system in ICP. As shown in this experimental result, RGB fusion works well in the geometrically under constrained case, whereas ICP-based Kinect fusion fails, resulting in poor reconstructions. The key idea of our frameworks are frame-to-model tracking by aligning an input RGBD image with the accumulated color volume and hybrid tracking that automatically select the complementary method according to the
Good afternoon, ladies and gentlemen. My name is Dion Sabetta. I work at the Council for Scientific and Industrial Research in South Africa. I'm here today to tell you about some work that we've done in bearings-only path following with a vision-based potential field. So the goals of the whole setup, we implemented a vision-based teach and repeat path following algorithm, and the intention was to use this to automate the return from a teleoperated inspection task. By driving the robot in to do the inspection task, the operator has already solved the hard problem of navigating in a potentially unknown environment. So if we can re-exploit this path to get the robot back out, we're in a good position. Our algorithm is feature-based and a mapless approach, and it uses only feature bearing provided by an omnidirectional camera, so we are constrained to a 2D manifold. The algorithm essentially works by minimizing the cost associated with the vision-based potential field. More about the potential field. It's a cost related to the distance between two images, and this cost is rotation invariant, which is quite important because it allows us to follow the path in both directions. The potential field is calculated directly from the matched feature coordinates or bearings in two images, and it's essentially the variance of the differences in feature bearings. The controller that we use is designed to minimize the current value of the potential field. It's roughly based on the work of the pure pursuit algorithm or the driving with tentacles algorithm from Coultier and von Hundelhausen, respectively. Basically, we consider a number of candidate paths, evaluate the predicted cost according to the potential field of each of these paths, and then execute the best looking path or the one with the lowest cost function. This, however, requires forward prediction of the feature locations, which can be troublesome over long horizons. If you have a look at the results on the right-hand side, you'll see that from 0 meters to 1 meter, to 3 meters, it starts degrading quite badly, and at 5, the path is barely noticeable. To overcome this problem, we adapted the controller to work well with a short look ahead, essentially by pre-filtering the reference signal. A couple of results. We demonstrated the algorithm in both urban and extra-urban scenarios with path lengths of around about 400 meters or a quarter mile. The red path in those images represents a taut path, and the other colors are successive repeats. The ground truth was provided by a differential GPS system. If we have a look at the actual results or the error of each of the path following things, we have the sort of blue and green paths there indicating the path error, and the red sort of representing the 1 sigma GPS accuracy. From this, you can basically infer that the accuracy of the system is roughly on the same order of magnitude as differential GPS. That brings me to the end of my talk. If you have any additional questions, I'll be pleased to answer them in the interactive session. I thank you very much for your time.
Hi, I'm going to talk about event-based post-tracking for high-speed robotic maneuvers. My name is Elias Mügler, and this is work together with Basil Huber and Davide Scaramuzza at the University of Zurich. So we are looking at visual tracking of high-speed robotic maneuvers, such as quadrotor flips that you can see in that video, at rotational speeds of up to 1,200 degrees per second. But we're not just interested in flips, but this is just the case we're looking at for this work. So when we look at the front-looking standard camera of that quadrotor, we can see that the images suffer from heavy motion blur effects. So we try to overcome this limitation by using a different vision sensor, namely the dynamic vision sensor. This revolutionary sensor has independent pixels that asynchronously report brightness changes at the time they occur, with a temporal resolution in the range of a few microseconds. So when we now look at the disk, a rotating disk with the black dot on it, we see that the standard camera output gives us full frames at the fixed frame rate. A DVS instead looks as a spiral in the spatial temporal domain. Now, if we stop that disk, nothing changes in the scene, so the DVS will not output any events, while a standard camera wastefully sends full image frames. So now if we speed up the dot, we see that we have motion blur in the standard camera output, but the spiral in space and time is just squeezed, so a DVS can handle such fast motions. What does that look like in real scenes? So when we have the camera static and move something in front of it, we can only see those changes. When we move the camera, we see the gradients in the image. So what we did in this work is we put the DVS together with a standard camera on a quadrotor and performed flips in front of a black square on a white wall. And now, when we play that a bit slower, then we can see that when we render the output of the DVS appropriately, we can still see the sides of the square rather sharp. However, this is only a rendering of the output of the DVS, so we integrate or accumulate all events that happen over a time interval delta t and display that in the same frame. But every single event that you see in this frame has its own micro-resolution timestamp. Now, we want to move from frame-based computer vision algorithm to event-based computer vision algorithms, what means that we want to update the state of the system whenever a new event arrives. I have a DBS with me, so if you want to play around with the sensor, come visit me at the interactive session, and there I'm also happy to share all the details about the algorithm we used for tracking there. Thank you.
Hi, my name is Nick Calavarz-Bianco. I work with Ryan Eustace at the University of Michigan. So today in this work, I'm going to be focusing on the problem of feature-based image registration. And in this situation, we're going to be matching feature descriptors that encode the local appearance of an image. This allows one to estimate the 3D structure of the scene and the motion of the camera, and it has proved to be a very useful tool in computer vision. Unfortunately, changes in lighting can drastically affect the local appearance of an image. And as we can see in this example, something like this could cause matching between features extracted with SIFT or SURF to fail. And if we consider this challenging data set that we're working with, which was collected by a robot in 27 sessions over the course of 15 months, what we see is that even though there's lots of changes in appearance due to weather and construction and the changes of the seasons and things like that, most of the time it's lighting throughout the day that's affecting whether or not we're able to match. In actuality, with SIFT and SURF, we're only able to match about 20% of possible pairs in this data set. So what we're going to propose in this work is a method to learn feature descriptors that are more robust to changes in lighting than standard hand-designed features like SIFT or SURF. The first step in this process is to observe how changes in lighting affect the local appearance in images. So in order to do that, we collected time-lapse videos and then tracked local patches through these time-lapse videos in order to observe how they change. We then use pairs of matching and non-matching patches to train a convolutional neural net with a contrastive loss function that encourages matching patches to be close together in feature space and non-matching patches to be far apart in feature space. When we compare the precision recall results of our proposed methods, which are shown in red and green, with SIFT, SURF, and a learned version of DAISY, we see that our descriptors provide a significant improvement over SIFT and SURF, and that they degrade more gracefully as there's a higher variance in lighting, especially in this high precision region where you would like to work with feature descriptors. And if we go back to this data set I mentioned previously, we're now able to match about 30% of possible pairs, which is a 50% improvement over SIFT and SURF. So we think that these are promising initial results, and I'd love to talk about them with you at the interactive session.
All right. Hello, everyone. Today I'm going to talk to you about detection of small moving objects using a moving camera. Unfortunately, Moin was not able to come here today, so I'll be presenting on his behalf. And so in this method, what we have is, given an input image, we'll be doing some motion recovery and background modeling, along with some refinement and using tracking in order to discriminate false positives in order to create to find the moving objects. And so for the motion recovery, what we do is we get a two-level registration that is applied using wavelet coefficients. And we use an affine registration to perform the global motion compensation, and then freeform deformation to register the pixels locally. And it might be a little bit weird that we're using wavelet transformation for this, but we found that it's giving us better results when compared to other approaches, such as Gaussian pyramids. And so in the two-level method that we're doing, we first use the first level for non-rigid registration, and in the second level, we do the affine registration. For the background modeling, we're using an adaptive GMM, and by looking at the differences across different frames, we are able to get candidate pixels for the foreground. And then once we have the candidate pixels for the foreground, we can do some refinement, and we do this with a simple thresholding on a component-based refinement. And then for a pixel-based refinement, we're using HMMs in order to further discriminate erroneous pixels. And then finally, we're doing some tracking by using a particle filter, which further removes false positive foreground pixels. And here are some of the results that we have so far. We've done experimental tests, both indoors and outdoors, with moving cameras. So this is a couple of pictures from the lab at the university. We also have some aerial video. showing the motion within the video, variable focus, focal length in an outdoor environment, and some other high motion videos. So here's a quick video showing some of the results. Here you can see, although it's getting really good results when tracking the person moving around, the shadow is actually a problem that we haven't been able to address very well. And so if you do some masking here, you just see a shadow moving around. It's a little ghost. And so this is one of the examples for outdoors. We also have faster motion. So in here, in aerial video, you can still see the cars being modeled and found, the motion that video is being found properly. And so since Moin was not here today, if you're interested in this, I encourage you to take a look at the paper and contact him if you have any other questions. Thank you.